Well, I'm going to be showing you how you can run a single patient level prediction model by using the patient level prediction version 6 in the Odyssey packages, set of packages. So I'm going to show you this with the example of the Eunomia simulated data set. So this actually, if you use the package Eunomia, you can install through remotes and then install GitHub and then Odyssey/Eunomia. I write this out here. So you can install Eunomia using remotes, install GitHub, and then you just need to type Odyssey and then Eunomia. If you run this bit of line, this will install Eunomia and you'll be able to have some simulated data to actually try out all the different codes that we have in the Odyssey Hades library. So I already have Eunomia installed. And if I run this function, get Eunomia connection details, this is going to create an SQLite connection. And it's just already created that. So this now is my connection details to an SQLite database that was created with this function. If you were using your own data, you would need to use the database connector function, which is create connection details. So if you were running this on your own data, you would need to use this function, and then you would need to specify all this information about your connection. So the database management system has to be one of the supported ones you can see on the list here. Your username, your password, the server, the port, and then sometimes you may have to add in some extra details. But Eunomia has a function that creates this for you if you just want to test some code. And then because we're using Eunomia, we actually need to create the data set. So we call this function create cohorts in Eunomia with the connection details that we just created here. And what this is going to do is it's going to create some cohorts and some OMOP CDM data into this SQLite database that was created previously. So if I type this here, you'll see that actually very quickly created lots of different cohorts. So there's 4 different cohorts here, 3 for drugs and 1 GI bleed. So we have 1 outcome. You have a little bit of information about this. Now, this is quite small data, but we're just going to be testing it. Again, if you were to run this on your own data, you would need to have your OMOP CDM database, and you also would need to have created some cohorts that you want to use for your prediction, either as target populations or as outcome cohorts. But if you're following with the Eunomia, it's just these few lines, and then you can actually get some data to practice with. Now, the next thing for patient prediction is you now need to create database details. And what this is going to have your connection details that we just created here for Eunomia. But if you had your own database, you would need to put these in here. And then you need to have information about where your data for your OMOP CDM databases are found. So what's the schema? Now in Eunomia, the schema is main. So for Eunomia, for every single schema, whether it be the CDM or where your cohorts are, your outcome and your target cohort, you need to put main in here. The CDM database name, this is just for your own reference, a name of the database. So I put Eunomia here and an ID. Again, I also put Eunomia. And this is going to actually be used if you end up using the tools like Strategist, which we're developing. This actually needs this is quite important for Strategists. So this is why we have a bit of redundancy with a name and an ID, because the ID is going to be used for Strategists, although in this example, it's not. Then we have to say what our cohort table name is. So the table that contains the cohorts for your target population and your outcome. And these can be generated through things like Atlas. And in Eunomia, that cohort table is just simply called cohort. So if you're using Eunomia, you can just fill out the exactly same values that I've put here. If you are using your own data, you need to know what schema your OMOP CDM database is on, what schema that your cohorts are generated into, and the table name for where your cohorts are. And they can be the same for the outcome in your target population, or they can be different schemas and different cohort table names. Then the next thing you need to do is you need to specify your target ID. So the ID for the cohort you want to do the prediction for. In this case, I've picked NSEDs. So I'm going to be using a target population of NSEDs, and then you need to specify your outcome of interest. This can be 1 or this can actually be multiple outcomes if you have multiple outcomes. But in this case, we actually have 1, which is the GI bleed, and this was a cohort ID of 3. So I put in NSAID ID and GI bleed ID. So if I run this, I'm actually just going to have a settings now that has all the information I need now to tell me where everything is for extracting data. So the next step is to now extract the data. So PatientLevelPrediction has a function get PLP data. And this takes as input your database details, so we know where all of our tables are found. And then we also have a covariate settings, and this is going to specify what covariates you want to create for your target population. So there is an ability to customize this, but what I actually recommend for most cases, you can probably use this feature extraction create covariate settings function. And this has a lot of different options you can pick. So you have things like gender, age, race, ethnicity, index year you probably don't want to use for prediction, but index month, maybe if there's seasonality effects. And then you can use things like condition occurrence. So this is basically going to create variables using the condition occurrence table in the OMOP CDM. And you've got different time periods. So anytime is basically saying, did they have this code anytime prior? 1 if they did, 0 if they didn't. And then long term is just looking in the last 365 days prior to index. Medium term is looking at the last 180 days prior to index, and short term is the last 30 days. Although there is actually an input in this function to change long term, medium, and short term. So you've got some flexibility there. But you can see you've got things like conditions, you've got drugs, you've got procedures, devices, measurements. You can select as many of these as you want. Bear in mind, if you're doing a prediction, if you don't have big data, so if your target population isn't big, if you have too many features, then you may actually struggle to fit the model. You probably will be very likely to overfit. Because I'm showing this example of the Eunomia data set, this is actually a very small data set, so I don't want to select too many of these because I know I'm going to get a bad model out if I do that, most likely. So here I've just selected that I want to use gender, and I want to use age groups, and I also want to use conditions. So this is actually condition group means you're using the hierarchy for the SNOMED to know the relationships between parent code and child code, and it's actually using that to kind of group things up into higher levels. Now, like I said, there is customization. You can create your own SQL to extract whatever features you want. You're not tied to these features. If you wanted to do that, then there's documentation in the feature extraction package on how you can do that. But I'm just going to use the standard settings for now in this example. And then the next thing is this restrict PLP data setting. So this is something that you don't have to specify. If you don't, it's just going to use, you can basically just use the default for this, and it's just going to not do any restrictions. But if you wanted to do your prediction using, say, just 2010 to 2020 data, rather than all the data in the database, you can specify basically a minimum date for your target population index to be included and a maximum date. So if you wanted to do your prediction just using 2018 data, you could change this to 2018, and then you can change this to 2018 with December. So you'd want to put December here and maybe 31 here. So this would basically say I'm only going to take people from the target cohort if their index was in 2018. Generally, I actually don't enter these. I normally often just take all the years, but if you want to, that's an option in this restriction. And I'm going to show you the other options you have. So there's also first exposure only. So if your target cohort was all exposures of the drug, so we're looking at NSAIDs. So maybe someone could have NSAIDs multiple times in the target cohort. If, for example, you wanted your prediction just at the first time, you could set first exposure to true. And this means that when you're extracting the data, it's basically going to only look at the first time someone had the drug rather than every occurrence is going to get downloaded. And then the next thing is washout period. So this is basically saying the minimum number of days prior to that index date that they have to be observed in the data. Generally, we recommend using about 1 year washout period. So they have to have been in the database for at least 1 year, which means you've got 1 year's worth of data capture to describe the patients and use as their features. If you had 0 days, you would have no features for that patient. So you do want some minimum restriction here. Sometimes this will be put into the cohort definition itself. Although as a best practice, it's probably better to do it either at this stage, or there is actually another option of doing this after you've downloaded the data. You can also set a washout period. That gives you a lot more flexibility because you can actually download the data once and see what impact different washout periods makes. And then you've got sample size. This is if you have a very big target cohort and you don't want to spend hours downloading the data. So say you had 10 million patients and you knew that's going to take a few hours to download, you could actually run a preliminary analysis where you just sample, say, 100,000 of that 10 million sample, just to quickly get the data, quickly do a model, just see how feasible the prediction is. If time's not a limit, then you probably just want to not put any sample. Although there has been some research in the Aussie community into learning curves, and you'll see actually there is a certain point where adding more data doesn't gain you anything, and it will just slow things down. So you may want to actually do some sampling if, for example, you know you're at the point where adding more data doesn't gain you, it's just going to slow things down. Because I'm doing a very small example, this actually isn't going to do anything, because I'm pretty sure that the cohorts we have are less than 100,000 anyway. But these are the three things. So we already specified database details, and I've run through the others. So now if we run this, we're going to get our data extractor. So this actually just executes some SQL based on the database details that we specified here. And it's actually extracted these features that we specified here for everyone in our target population, which was ID4, which was the NSAIDs. We also extracted for these people who have the NSAIDs, every occurrence of the occurrence in cohort 3. So basically every time they have the GI bleed recorded for those patients. So if we look at PLP data, we can actually see what these people look like. So we have a cohort table. If we type view here, that'll pop up that data frame. So here we've got a row ID. So this is a unique identifier. Subject ID is unique if you said first exposure. But if you didn't say first exposure, you could have someone in multiple times, which means the row ID is unique all the time. Subject ID isn't necessarily unique. It depends on the settings. Then you have that index date that they were into the target cohort. You have information like how many days had they been in the cohort at index, so that the days from observation start. So these have been in for quite a long time. And then you also have information from cohort end. This depends on how you've defined your end date for your cohort. So if your cohort end date is the same as your start date, this is always going to be 0. If you had your end date defined to be while you're exposed, so start of the drug exposure to the end of the drug exposure, then you'd expect this to be some other positive value. Then you have your time for the observation end. So this is how long from this date until they never get observed again. They've left the database. Their age index and also their gender index. So this is the target population here. So for everyone who basically had the NSAID in that data set, we simulate data set we're looking at. Now we can also do the same, and we can look at outcomes. And what you'll see is the outcomes has this row ID again. Outcome ID, because you can actually specify multiple outcomes when you download the data. And then it has a time, basically the number of days from the cohort index for this patient until they had this outcome. So if the days to event is positive, it means that they had the outcome, the GI bleed recorded that many days after they started their NSAID in this example. And people could be they actually could have multiple occurrences of the outcome if the outcome, depending on how you define your outcome. So if your outcome is first time that you experience the outcome, then you're only going to see 1 row per person. But if you defined your phenotype in your outcome phenotype to allow people to be in multiple times, then they could actually have multiple rows here. And what happens is we use these data frames to do the labeling. Did the person have the outcome within the time at risk, so the time period we're trying to do the prediction for? These are what we use to figure out how to label people. Then you also have information about covariate data. So because we can have quite big data sets that we download, this covariate data actually gets stored as what's known as an Andromeda object that's currently, but this could be changing in the future, has an SQL-like backend to it. So this just means that we can have these big data sets and play around with them in R without having the memory issues that you could if you were trying to have everything directly in RAM. So the main thing here is the covariates. And if I do as.data.frame, you don't want to do this if you have big data, because like I said, this is going to convert it to make it go into your memory. But if this I know is small, so my computer can handle it. The covariate data covariates basically has a row ID, has a covariate ID. So this is a feature. So each of these is basically going to be a feature. Each unique covariate ID is a feature, and then their value. Most of the features we have from feature extraction are binary. They're 0 if you don't have it, and 1 if you have it. So this is saying that this person had this covariate. There is logic to these covariate IDs. The last 3 basically corresponds to the type. 210 is a condition group, because you saw when we actually defined our covariates, we used the condition group error long term. Basically anything from these features has 210 at the end of it. So the last 3 digits of a covariate ID, if it's from feature extraction, standard covariates will be the analysis, and then the numbers before that basically tell you a concept ID. So this is how things are, the concept that's recorded in the database in this case, the condition table. We represent this in sparse data format, so we don't keep the zeros. We don't need the zeros because we only really need to know the ones. If you have something that's not binary, then you'd actually have every value that would be there for each person. But most of our data are binary covariates, so we actually can get rid of quite a lot of the rows that are 0 because we don't need those stored in this object. So that's what the PLP data looks like, and we're going to be using that to create our label data to learn our model. However, in version 6 of PLP, what was newly added was this diagnose PLP function. And this diagnose PLP function will let you see whether there's any flaws in your model design. So in version 6, things are a little bit more model design centric. The run PLP that I'm showing hasn't been changed too much, but you'll see if you watch the tutorial on the multiple run PLP that actually you're going to be using lots of different designs, and designs consist of your type, population, and outcome that you define to create your PLP data, and your covariate settings, your population settings, and this is just some additional inclusion criteria plus your time at risk, your split settings, so how you want to split your data into test, train, and validation data sets, any sample settings, so if you wanted to over or under sample. We've done research in Odyssey to show that this probably isn't a good idea, so that's why I've actually not used this here. I've set this to null, but if you wanted to, that's an option. Any feature engineering, again, I haven't actually done any here, but we've made it so that that's possible now. I believe this was new to version 6 as well. And then pre-processing, do you want to normalize your data? Do you want to remove any extremely rare features? Model setting, what classifier do you want to fit, or survival model? And then you have a save directed to save things. But these things are what makes up a model. So these are your model designs. And what we'll be doing from this function diagnose PLP, given these settings that you've specified, it's going to check to see if there's any major flaws. So are your covariates overlapping with your time at risk? Have you introduced some sort of bias from doing some inclusion criteria? These are the sort of things that the diagnose PLP is going to tell you. So it will tell you straight away if there's any obvious errors, and also that you explore to see if there's any other more hidden issues with the design. So for this prediction task, our outcome is the GI bleed. So that was outcome 3. So we have to put outcome ID 3 in. We put in our PLP data that we just downloaded. So we have PLP data here. We're putting that into this function. We need to give it an ID. So I just called it example run single PLP. This is actually going to be used when it gets saved. Then the population settings, as I mentioned, this is a mixture of additional inclusion criteria that you're doing after you download the data, and the time at risk. So when you're trying to predict the outcome occurring. So there is a bunch. I believe I've picked most of the main ones actually. So there's a bunch. The main one is the first exposure only. This is saying, do you only want to look at the first index, the first day that was indexed for the cohort? So for NSAIDs, if someone was in multiple times, do you want to just restrict to the first time? Yes or no? If you do, true. If you don't, false. Again, this depends though on how you define your cohort. So this is going to be if your cohort is already restricted to first time exposure, this isn't going to do anything. So this really depends on your cohort. But if you've got no restrictions on your cohort, then this will then add an additional restriction to say first time only. The washout period, as I mentioned before, this is the number of days prior to index that they have to be into the database before index to be included. We generally say 365. days, so a year, but you can actually specify this to be whatever value you want. So you could say they just have to have 60 days of prior observation. This is only going to, again, be used depending on how you defined your cohort and if you've used any setting when you've downloaded the data. So you could have specified that in this setting. So this is only going to occur after all of those. Then we've got remove subjects with this prior outcome. So what this is saying, sometimes if you're trying to predict an outcome, you may want to try and predict the first occurrence of that outcome. If someone's had the outcome recently, you may not want to include them because actually your outcome may actually just be a continuation of what they already of an illness already have. So it's pretty good to have some filter here with the outcome. So often you will remove people with the prior outcomes, and you may say something like they kind of had the outcome in the last 30 days or the last 6 months. So you can specify that here. If you want to have it so that they can never have had the outcome prior, so we're going to remove anyone from the target population if they had the outcome, then just put a really big number here. And this is going to say we're removing anyone if they've had the outcome anytime prior. For now, I'm just going to keep it to 180 just for this example. And then there's this required time at risk. And what this means is, do you want people to only be included if they're observed for the whole time at risk period? So if we're doing the prediction to see whether they had the GI bleed in the next 1 year, if someone leaves the database after 6 months, how do you want to handle them? We used to have it set so that you would have required time at risk equals true, and that means that people who drop out before the end of the time at risk actually get excluded. But we did some research and we actually showed that if your time at risk isn't too long, it's probably good to actually just have this set to false. There's going to be some calibration issues potentially, but it actually is better in terms of discrimination, and otherwise you can actually have settings that can bias a model. And if you're interested in that, there's these papers are on the website that give you some information about that. Then the last thing is your time at risk settings. So when are you trying to predict the outcome relative to the target index day? So these examples here, I'm saying 1 day from the target cohort start date. So 1 day after they have their NSAIDs is when the prediction time risk starts. And the prediction time risk ends 30 days after the cohort starts, so 30 days after their NSAID start date. So I'm basically predicting the GI bleed within from 1 day after they start their NSAIDs to 30 days after they start their NSAIDs. Now you can actually do something like cohort end here, and if in this example, now if I used cohort end, I'd actually be predicting whether they have a GI bleed while they're taking the NSAIDs, or 1 day after they start taking the NSAIDs, up to the end day that they're taking the NSAIDs plus 30 days. So this all depends on how you've defined your target cohort and how you've defined your cohort start and cohort end dates. I'm going to put this back to cohort start. Split settings. This is how you want to split into test train validation. By default, you have a test fraction of 25%, I believe. Train fraction will be 75%. You'll do, it will give a random split seed, but you can specify this if you wanted to control that. And then number of folds is 3. And the type will be stratified. So what this means is that you keep the outcome proportion the same in your test train and your folds when you're doing cross-fold validation. You can change that, and there's also an option to have a completely custom split setting if you wanted. Sample settings, if you wanted to use this, you can actually write code to say how you want to do over or under sampling. So I mentioned this isn't generally recommended right now, but there is the ability. If you look at the website, you'll see how you can actually write custom stuff for this. Feature engineering, the same. Right now, there isn't anything really in the package for feature engineering, but if you wanted to manipulate your predictors before they actually get used by the model, you can actually write some custom code to do whatever you want. Again, there's examples on the website. Pre-processing, this is just going to say, do you want to do normalization, which is by default true. Min fraction is basically saying what fraction of the target population must have an outcome, at least this fraction must have, sorry, not the outcome, the covariate, the predictor, for it to be included. So what this is going to do is if you set your min fraction to say 0.001, so this is 1 in 10, this is 1 in 100, this is 1 in 1,000. You're basically saying if the predictor is rarer than occurring in 1 in 1,000 of the target population, we're going to remove it. If you wanted 1 in 10,000, you just add another 0 here. So this can control how basically do you want to get rid of rare covariates. This is handy if you've got small data and you're trying to actually just get rid of the covariates a little bit to speed up the training. But there's nothing wrong with setting this to 0. So if you wanted to, you could set this to 0 and you keep everything, no matter how rare, and just let the model pick it. Remove redundancy. You should set this to true. This looks and says, are there any features that are completely correlated? And if so, remove them. This is good just because you don't really want correlation, especially if you're doing things like logistic regressions. Then you've got model settings. Here, what I've done is I've picked a lasso logistic regression model. You can actually pick from a bunch in the library. So what you'll find is if you use the set and then you press tab, it will tell you basically all the functions in patient prediction that start with set, and most of these are actually going to be models, either classifiers, binary classifiers, or survival models. So we've got ADA boost, we've got Cox regression, we've got decision trees, gradient boosted machine, iterative hard thresholding. So this is the logistic regression type of model, which is a generalized linear model that basically lets you select how many features you want, which is quite nice. KNN, lasso logistic regression, so logistic regression with the lasso regularization, multi-layer perception, naive Bayes, random forest, and support vector machine. So these are all the classifiers or survival models we have already built into the package. But if you want to add your own, there's also a possibility for you to write custom functions. So you could write your own set function, your own fit function. And again, there's documentation on the website for that. Basically, the package is written in a way that you can customize anything that you need to, except for things like evaluation metrics, because we want these to be fixed to make it so we can compare. Then the last thing here is just the save directory. Where do we want the results to be saved? So if I run this now, what this is going to do is it's going to run the diagnostics. So it's looking at the data and it's looking at different checks to see whether there are potential issues in the way we've designed this. So in our population settings and our inclusion and our time at risk and the way we've done split, if we've done sampling, feature, it's going to check all of these and just see and give you a flag if there's any issues. The output will just be, I believe there's a summary, and this will just tell you for the PROBAS criteria, whether you pass. Pass means you did, 1 means you pass as well. Unknown means that there may be some issues. So for example, this could correspond to information about the size of the data, and sometimes you don't know if there's enough data. It's kind of an unknown. If you have lots of data, you know it's good. If you have too few data, you know it's bad. But there's some kind of middle ground where you don't really know, and you might want to kind of do some additional checks. So it's a bit more subjective. So this is the current output, and then there's also plots, and you get some information about the different types. So this is based on the PROBAS criteria, and PROBAS is split into participants, predictors, outcomes, and design, I believe. So this is just giving you some information. Design or model analysis, or the design, that one you can't really check until you've got the model fit. So that's kind of like after model checks, but before that, these are the things that you can actually check to see if there's any issues. So you can dive in a little bit deeper. It's actually the Shiny Viewer where you can really get some insights from this. So I'm going to be showing you the Shiny Viewer in another video, and that will actually give you a bit more information about how you interpret this diagnostics. Then once you've got the diagnostics, once you're happy, the next thing is the run PLP. So it's the same function that was in earlier versions of PLP, but the inputs may have changed now because we've got more model design centric, and we've also added in more options. So feature engineering, sampling, and some of these other options weren't available, and it wasn't possible to customize as much in previous versions. Now you've got the ability to customize, and you have a lot more options. So these are the same inputs as we had for the diagnostics. You put in the same values, but what this is going to do, rather than just checking to see if there's any issues with the design and the database you've chosen, this is just going to run the model. So if we run this, it's going to fit the model that we wanted based on our designs. So based on the time at risk we said, our outcome, our target population, and all of these settings, it's fit a model. It's going to evaluate that model doing whatever internal validation you specified in your split settings. And then it's going to return those results. So if we go to PLP Result, we're going to see that we have an execution summary. So this is just information about how long it took to fit the model and the system that was used to run them to fit the model. You've got your model yourself. So this is actually the model design, which has all of the settings that you specified. The nice thing about this is everything you need to redo your analysis. So you could, if you share your model with someone, they've got all the information they need if they combine with the patient prediction package to replicate the same settings that you did, the same model design, and develop a model on their data. Or if you had the same seed, if you all of this information actually has the seeds, you could rerun this on your data to get exactly the same model out. So this is completely transparent. You've got all the information you need here to share. And then the model itself, depending on the type of model, will either be a data frame or it'll be a link to a file that contains the model. In this case, it is actually effectively a data frame that will get used if you want to apply the model. And then you have information about the pre-processing. So here you'll have information about any feature engineering that was done. So this will keep the function for the feature engineering that you've basically learned. And it means that if you were to apply the model in new data, it can apply the feature engineering function. It also tells you if you need a dense matrix to apply. Some of the classifiers needed a dense matrix. And the tidy covariates, this is where the nice thing is it tells you any covariates that were deleted from redundancy or due to infrequency. So you've got information here to basically pre-process the data the same and the norm factors, so you can do the normalization the same in the new data. So this is important. You need to be able to do the pre-processing when you apply the model on new data. Then you have train details. This just tells you information about the analysis ID, like you specified, the database that was used to train the model, attrition, training times, hyperparameter search information, and final hyperparameters. So this is just information that you of interest that you may want, you definitely want to keep. And then covariate importance, this just tells you if there was the ability to do feature importance with the method that you chose, the classifier you chose, or the survival model you chose, that will be here. And you have a data frame that will say, here's a covariate, here's the name, and then you'll have the covariate value is basically the importance. So that is the model. And that is, you can give that to someone else and they can actually then just apply it to their data for external validation, which is pretty nice and easy. You've also got prediction data frame. So if you actually wanted to see people's risks in your target population, you actually have here, actually, let me just view this one so you can see what this looks like. So you'll see for every person in your target population, you have the same information as we saw for our target population, except now you have a column that says whether they had the outcome. 0 means no, 1 means yes. You have information about how long the time at risk was for them. And then days to events, if they have the outcome, the days to event would be a value, in this case less than 30, because we had a 30-day time at risk. And then we have a value that tells you their predicted risk. So we can order by descending order, and you should hopefully see a lot more O's popping up here if the model is done well. You also have information about the evaluation type. So you have a test. That means that they were used in the internal validation only. You have a train. That means they were actually used to fit the model. And then you also have information about cross-validation. So sometimes you may want to skip doing a test and you may just want to do cross-validation. You'll have that in here as well. So depending on the split type you did, that will kind of tell you what values you can have in your evaluation type. So you've got your model, you've got your prediction, and the main thing is this performance evaluation. So here, if we go to evaluation statistics, you're going to have information about how well the model did, just the most common metrics, the just kind of single metrics like the AUROC, You've got confidence intervals, you have the error and precision recall curve, the Brier score, you got the information about calibration, so like the E average, E90, and E max, calibration at large. So we have a lot of information here, just summary information about how well the model did. And again, you have that for each of your evaluation types. So we have the test, we have the train, and we have the cross-validation for that. Also have information that will be used for plotting. So things like the threshold summary, this can be used for plotting the ROC plots and the precision recall plots and such. Demographic summary, it can be used to tell you, and you can do plots to see how well the model's calibrated across ages and sexes. And then calibration summary will tell you how well the model's calibrated in general. And then prediction distribution, this actually can be used to do these like box plots and distribution plots to see how different the predicted risk distributions are for people who have the outcome and don't have the outcome. So this is the main one for exploring the model. It's much nicer if you use the Shiny viewer than doing it manually. But I just want to show you what's in there. And then the covariate summary, this is just giving you the information about the covariates that are in the model, how common they were for people with the outcome, without the outcome in the test set and the train set, and the covariate importance. So this is here, it's just, this is a big descriptive summary of all the covariates in the data. Then we have the analysis reference. So this is just information about your analysis ID and your analysis name. So this is just more for just tracking the model, and if you're sharing it, you can see if the analysis, you can check this, you basically can have a reference for your model. So this is everything that's output. And then the last thing really is once you fit the model, you can use this view PLP. So if you've done a run PLP, you use a view PLP, and then you put in your run PLP result, and you can choose to put in your diagnostics if you had it. You also have an option of putting in a validate PLP if you did an external validation. There is a function in PatientLevelPrediction, external validate. So this function here, external validate PLP, takes as input your model. So this would be the PLP result $model. It's what you'd put into here. And then you can put in new validation database details. So you create those database details, but for your validation database, you can put in new validation restriction settings, and you have information here about how you want to do recalibration. So there's some settings here for recalibration, and it's as simple as that. With those input, you can then just press enter, and it will apply this model to your new data. And the way it can do that is because, as I mentioned, this actually contains everything you need. It has the pre-processing, it has the model design, it has everything you need to basically apply this model to new data in the OMOP format. So this is another one. If you ran this, you can also have a validation, and you can also put that into your Shiny for the validate PLP. And then if you run this, this will actually pop up a Shiny viewer, and I'll be actually showing you how to interpret this in one of the next videos.